there's another dependence on sigma 1 that comes from the determinant of the C costs. Okay, in general, there's an additional source of dependence on sigma 1 that comes from the determinant of the C costs.
Can you tell me what compels us to take an average like this?
What compelled us? Nothing compelled us.
We could have just taken an average.
We could have just put it at a fixed position. This is the same answer. That's what we're saying, right? We're saying whether we put it at one position or another, we get the same answer. So might as well average over the whole thing. And the point is that the averaging does not have an extra weighting with respect to sigma from the determinant. So the reason we're doing this is to put these all operators manifested in the same situation. In this case, we can. Is this clear? Okay? Yeah. Okay, fine. Well, yeah. Fine. So now we've got a nice formal expression for correlation functions of the torus, which is supposed to integrate over the fundamental domain of the torus, and it's supposed to put in these insertions of C tilde, B tilde at some points of the torus, and we put in the vertex operators as we want. All matter vertex operators are integrated, and we're very happy. Is this clear? Okay. Now, the next thing that we have to do is to evaluate what the matter vertex operator correlation functions are. Okay. So the first thing that we're going to try to do, and in the case of the torus, this will already have physics in it. That will already be actually we're going to evaluate no non-trivial correlation. Well, no scattering amplitudes of the torus. However, what we are going to do is to evaluate the partition function of the torus. Okay. Now, see, what does that thing mean physically? You see, what we're doing on the torus is a one-loop diagram. So when we evaluate the partition function of the torus, what are we doing? What is a one-loop diagram with no insertions? What's a one-loop diagram with no insertions in field theory? In free field theory, what does it compute? Vacuum energy. It computes the constant part to the. Okay? So what we will be doing is evaluating the vacuum energy of string theory. Actually, we'll do better. We'll take string theory in Euclidean space, put the time circle on a finite circle. Take the time circle, the x0 circle, put it on a finite circle, and then do these one-loop diagrams. Then what will we be evaluating? Yes, we'll be evaluating the partition function, the free partition function. So you see, unlike in this tree level case, when we go to this one-loop order, okay, there's already physics. See, there's already physics just in the vacuum element. In particular, what we get is the partition function of string theory by evaluating this vacuum amplitude once we've taken the time circuit on the Euclidean space and made it compact. Okay? So the focus of this lecture, well, what remains of this lecture, which is not very much, soon, we'll stop soon, and the next lecture will be to perform just the vacuum amplitude, just the amplitude on the torus with no insertions. Okay? And that already has physics in it. It corresponds to the vacuum energy in one limit, or more generally the partition function of string theory at finite energy. Okay? So this is the thing that we will be evaluating carefully and trying to see get general lesson. Okay, so I'll just take 5 minutes more, but in these 5 minutes what I want to do is to quickly start setting up what we need to compute. In order to get this. So what remains now, we have no vertex operators, all we want is the path integral of the matter center and the path integral of the BC system of the torus. Okay, now in general, it's pretty subtle, pretty difficult to keep track of this path integral without insertion. So ratios are easy to keep track of, but the path integral itself is in general subtle and difficult. It's possible, certainly, but it's sort of difficult. However, the torus, there's a very easy way to keep track of the answers by using the Hamiltonian interpretation of this conflict. You see, because when okay, let's first look at the rectangular torus. Suppose we have a rectangular torus like this. Okay, then we have this conformal field theory in space of size 2 pi. And what is this torus partition function calculating? Suppose this was 2 pi IA. What would the torus partition function be calculating? Give me a Hamiltonian interpretation of the partition function of a conformal field theory and a torus of this aspect ratio. Exactly. It's trace of e to the power minus 2 pi a times the Hamiltonian of the theory. Trace of e to the power minus 2 pi a times the Hamiltonian of the theory. Okay. When the theory is put on a circular line. Okay. Now, you see, more generally speaking, suppose the aspect ratio of this torus was sloped. Okay? Then, in propagating over, you would be propagating over a certain distance in the time direction. That fixes your temperature. That distance is the imaginary part of tau. Okay? But after doing this propagation, you identify your space with a translation. Right? So you take, you go up here and translate. That's the identification. Now, remember you were in a circle, so this translation was really a rotation. Okay? So, if you were computing the partition function on a torus like this, what would you be computing in Hamilton? Well, you would be computing trace of e to the power minus 2 pi and im tau times the Hamiltonian, okay, times the operator that translates you by 2 pi times the real part. Now remember, the translation generator was L0 minus L0 bar. This was the thing that generated rotation for the circle. And remember that H here was L0 plus L0 bar. Okay? So let's combine this up. So what do we get? We get trace of e to the power minus 2 pi, and then let's take the L0. Okay, so that's L0 into let's put it 2 pi. We get I times the real part of tau minus the imaginary part of tau. So let's take an I out here. I, so plus I. Okay, times e to the power 2 pi I L0 bar into what's changed is this thing. So that's we get a minus I here and real tau minus I times imaginary tau. Okay? So, suppose we the power I 2 pi times tau, and q bar is equal to e to the power minus I 2 pi times tau bar. Then what we found is that z of tau, the partition function on a torus whose modulus is tau, is the same thing as trace of q to the pi of 0, q bar to the pi of 0. But I've used that this thing is simply tau and this thing is simply tau. Okay? So great. We have this lovely physical interpretation. We have this lovely physical interpretation of the partition function of a conformal field theory in the torus. It's simply this trace, the trace of q to the pi of 0 times q bar to the pi of 0. Okay. Now we should probably stop this lecture here. Or should we just work out this kind of the free boson? Okay, let's quickly. 2 minutes. We work out the free boson and I'll ask you to work out the BC system is next. Let's quickly work out. Okay, so now what we want to do is for a single free boson to work out this trace. This is a very easy job because we know the Hilbert space of the free boson perfectly. So what's the Hilbert space of a single free boson? Well, it consists of harmonic oscillators of energies 1, 2, 3, 4, and then the 0 point. Let's first work out what we get from the harmonic oscillators. Okay, so if you've got a harmonic oscillator of energy of L0 energy 1, what is the partition function? Ignore 0 point energy in this because we deal with 0 point energy carefully. We do that separately. Ignoring 0 point. What do we get? What's that? What's the concrete in the vacuum? Q to the power 0. What's the concrete to the first excited state? What? And N0 is 1 for the first excited state. So Q, second excited state. Oh, 1 over 1. Okay. But the free scalar field has a harmonic oscillator of energy 1, a harmonic oscillator of energy 2. What's the concrete from there? Very good. 1 over 1 minus q squared. And also has harmonic oscillators of energy 3 as well. So what are we getting here? So the contribution from the harmonic oscillators is product, is 1 over product, n is equal to 1 to infinity, 1 minus q to the n. Okay, so we've dealt with the harmonic oscillators. Wasn't that simple? Okay, now the thing that we've not dealt with so far is the 0 point energy. Yeah, this would not literally be true of harmonic oscillators. It's only true once. I mean, there's all 0 point energy, which would in general be divergent. But we've understood how to deal with this divergence, right? And we understood what the right answer was, right? We understood that the right answer had for every harmonic oscillator a factor of q to the power minus 1 by 2. A factor of q to the power minus 1 by 12. Or was it 1 by 24? Oh, sorry, so it's 1 by 24. I think there was full energy that was 1 by 24. Apart from Q and from Q bar. Then, when we, that's Q to the power. 1 by 13. So what we've got here is, including 0 point, the contribution from 0 point energy, we've got q to the power 1 by 24 times all of this. Now, in string theory, we don't have one harmonic oscillator, we have 26. So what's the partition function when we account for the fact that we have 26 free oscillators? This thing to the power 26. Not at this stage. You see, what are our rules? We're doing the whole path integral. 24 has to come out as the answer, not in the input. Okay. Finally, what remains? What remains is the 0 volts. Okay? So what remains is the 0 volts. So now the 0 volts, we have q bar times h. And what is the contribution to the Hamiltonian for the 0 volts? Okay? The 0 volts we had, remember that it was the string theory effect, the string theory action was 1 over 4 pi alpha prime times x, what of that? Del alpha x mu, del alpha x mu. But we're restricted to the 0 volt. So this thing, this d2 sigma integral we just do, that gives us a factor of 4 pi, so we get 1 over 2 alpha prime times x mu dot square. This is exactly the Hamiltonian of a non-relativistic particle of mass 1 over alpha prime. So we have the same spectrum in this theory as for a non-relativistic particle of mass 1 over alpha prime. So what's the spectrum? The spectrum is no, this is the Lagrange m by 2 x dot squared. Right? So what's the spectrum? The spectrum is p squared by 2m. So it's alpha prime k squared by 2. Okay? And we have q bar. We have q bar to this form. Okay, so q bar. Okay, now let's write this out. So what was q bar? Q bar was 2 pi, so 4 pi times imaginary part of tau with minus sign. 4 pi times, was minus, so q bar was q bar is equal to e to the power minus 4 pi times in tau. Okay, so this thing becomes, so the contribution from 0 volts is simply d26k exponential of minus 4 pi and in tau times alpha prime k square by 2. Contribution to the partition function from the from 0 volt is simply this function. Okay, this is a Gaussian integral which we do, and after constants, which we keep track of the eventual answer at this stage. After constants, it's simply 1 over in tau the whole to the power 26 by 2, so 30. Okay, so what's the final answer for the partition function of what's the final answer for the partition function of what's the final answer for the partition function of the free boson? It's 1 over im tau to the power 13 Then we had q bar to the power 26 by 24, so 13 by 12. And then product n is equal to 1 to infinity, 1 minus q to the power n to the power 26 times product times 1 minus q bar. Now some number between. Okay? That is. So let me just confirm, and I think we'll stop here for now. Minus d by 24. Okay, let's switch. Looks perfect. Okay, so that's the answer, and actually Kuczynski has taken the trouble to keep track of the factors, and he has a 1 by 4 pi squared to the power 13 as well. Well, oh, did alpha prime cancel? That's a good question. Let's see, do we have alpha prime as well? No, we had 5, 4, 5, 5. Thank you. So the alpha prime, powers of alpha prime are easy to keep track of, same as the powers of even tau. The two pi's are probably harder to keep track of because you had 2 pi to the power 26 here. Okay, well, we'll trust Kuczynski for a second. Okay, fine. Now, as an exercise, I'm going to ask you guys to use the same technique to evaluate the BC, the partition function of the BC system. Okay, we'll go through it in class anyway next time, and then we will try to evaluate the full one-loop partition function of string theory on the torus at 0 temperature and finite temperature, and understand the physics of this. Okay, that's it. People who see it on camera have the right answer. So let me say this again. Sorry, so we messed up on factors of 2. Okay, so this QQ, when we wrote this as QQ bar to the bar Hamiltonian, should have been QQ bar to the bar L0 plus L0 bar by 2. So QQ bar Hamiltonian by 2, and so that the right formula has an extra factor of 2 here since these 2 cancels, and then all these factors are very easy to understand. The alpha prime to the power 13 is because the Gaussian integral from here. The Gaussian integral produces square root pi to the power 26. Then you get 1 over pi to the power 26. 1 over square root pi to the power 26 from here. Those cancel, and all the remaining 4 pi's are out from 2 pi to the 26 in the integral. Yeah. Okay. Sorry. Please continue.
If you did this computation in either like code or where you don't have a code, you just put 24.
Yes, if you did the calculation in Lightroom, you just put 24. But that's not our formalism. We're doing it in this full covariant way. So we should follow the rules. The rules say put 26, and then the rules say also include the BCCFT.
So it should match eventually with the
With what you get from Lightroom. But of course, this is much more strict in the sense that we know with what measure to integrate over the modulus of the tori and so on. All these things would be much harder to guess from if you want to be systematic. Well, yes. So in the end, we should get an answer that is that in the end sums only over